All right, today we're going way, way back to the very beginning. We're going to uncover the single most important building block of all modern AI. I'm talking ChatGPT, self-driving cars, all of it. It's called the Perceptron, and trust me, once you get this, everything else about AI starts to click into place. You know how Netflix just knows what you want to watch next? Or how your phone opens with just a glance at your face? It seriously feels like magic, doesn't it? But it's not. It's just math. And it all kicks off with this one super simple, super powerful idea. And believe it or not, the secret behind all that magic starts way back in 1958 with an attempt to copy the human brain. And to make it all make sense, we're going to use a fish. Yeah, you heard me right, a fish. Just stick with me here. It'll all make sense. So, to understand our fish, and by extension your Netflix queue, we've got to rewind the clock and look at the original blueprint for an artificial brain. So, this guy, Frank Rosenblatt, back in 1958, he has this wild idea. He's looking at a biological neuron, a brain cell, and he thinks, what if I could build one of those, but with math? He called his invention the Perceptron, and it was basically the world's first ever artificial neural network. And you can see just how literal that inspiration was. On the left, you've got a real neuron, it gets signals, and if those signals are strong enough, zap, it fires off its own message. On the right, our perceptron does the exact same thing, just with numbers. It takes in data as inputs, considers how important each one is, and if it all adds up, it fires an output. It's a brain cell made of math. So how does this digital brain cell actually, think? Let's make this super clear and just build one from the ground up. Okay, picture this. We're at the famous Jaffna fish market. We want to build a little machine that can answer one simple, very important question. Is this fish fresh or not fresh? It's a straightforward yes or no decision, which is the perfect job for our new perceptron. Now, our perceptron needs some evidence, some data. In the world of AI, we call these inputs. So for every fish, we'll give it 2 clues. First, the clarity of its eyes on a scale of 0 to 10. And second, how it smells, also from 0 to 10. These 2 numbers are our inputs. But here's the thing. Not all clues are created equal, right? At a fish market, you're probably going to trust your nose a lot more than just looking at the fish's eyes. The perceptron gets this. It uses weights to decide how important each input is. We'd give the smell a higher weight, telling our system, hey, pay more attention to this one. Then we have something called the bias. Think of it like a thumb on the scale. When it comes to food, we'd want our system to be a little cautious, right? So we can give it a negative bias, which basically means it starts off a bit skeptical. It's going to need a lot of good evidence before it's willing to say, yep, this fish is fresh. All right, so we've got our ingredients, inputs, weights, and a bias. Let's throw them all together and see how this little digital neuron actually makes a decision. The first step is just some really simple math. The perceptron takes each piece of evidence, each input, and multiplies it by its importance, its weight. So we get the eye clarity score times its weight, plus the smell score times its weight. This gives us a single combined evidence score. Then, to that combined score, we just add our bias. Remember our thumb on the scale? The final result is just one number. We'll call it Z. This is our final all-in freshness score. So we have our final score, Z, but what do we do with it? That's where the activation function comes in, and it's just a dead simple rule. If our score Z is a positive number, we output a 1, which means fresh. If Z is negative or 0, we output a 0 for not fresh. That's it. That is the entire decision-making process. And check it out. It actually works. Look at the premium fish. It's got great scores for its eyes and smell. The math spits out a positive 7.6, so the output is 1, fresh. Now look at the poor quality fish. The numbers are low, the final score is negative, and the output is 0, not fresh. It got them both right. Now, here is the really beautiful part. If you plotted every possible fish on a graph, with smell on one side and eye clarity on the other, what our perceptron's math has just done is draw a single straight line right through the middle. This is the decision boundary. Everything on one side of that line gets called fresh, and everything on the other side doesn't. Simple as that. Okay, I know what you're thinking. This is cool and all, but where did those perfect weights and the bias come from? How did it know exactly where to draw that line in the first place? In other words, how does this thing actually learn? Well, the process is surprisingly simple. It's basically trial and error. It starts out with just random guesses for its weights. Then it takes a fish it already knows the answer for, makes its prediction, and sees if it got it wrong. If it made a mistake, it just nudges its weights and bias a tiny, tiny bit to be a little more correct next time. Then it just does this over and over and over again with hundreds of examples. The whole secret is that it learns from its mistakes. Think back to that decision line on the graph. Every single time it gets an answer wrong, the perceptron just nudges the line a little. If it called a bad fish fresh, it moves the line to be a bit stricter. If it called a fresh fish bad, it moves the line to be more lenient, until, finally, it finds the best possible place to separate the two. So that's one single digital neuron. Pretty amazing on its own, but now let's zoom all the way out and see how this one tiny idea ends up powering the entire world of modern AI. So our little perceptron is powerful, for sure, but it has one major weakness. It can only solve problems where the good stuff and the bad stuff can be separated by a single straight line. For more complicated patterns, it just can't do it. It fails. And that single limitation is what sparked the next 60 years of AI research. People realized, hey, what if we don't just use one? What if we stack them up in layers? And that is how we went from a single perceptron to multi-layer perceptrons to deep neural networks and right on through to the massive transformer AIs we have today. And this, right here, this is the most important thing to take away. Every single time you use ChatGPT or see an AI-generated picture, what's really happening under the hood is millions, even billions of these tiny perceptron-like calculators all working together. They're all doing that same basic math. Inputs times weights, add a bias, get an answer. You now understand the fundamental atom of artificial intelligence. So we went from a single neuron idea in 1958 to a simple fish classifier. But that exact same idea, just scaled up 1 billion times, is how Netflix knows what you want to watch. You now get the fundamental building block of all modern AI. So the only question left is, what would you build with it?